Hello everyone. I'll be presenting our work on the power of interactive proofs for learning. I'm Mohammad Khodabande, and this is a joint work with Tom Gore, Muhammad Jahanara, Ninad Rajgopal, Bahar Salamatian, and Igor Shinkar. So our plan will be to make the Goldratt-Levin algorithm interactive. Goldratt-Levin finds all high Fourier coefficients of a given Boolean function using polynomial in T and N membership queries. So T here represents the number of high Fourier coefficients of a Boolean function. The interactive version was first discussed in GRSY, and they use polynomial in T and N random example as opposed to membership queries. Our work removes the dependence on N, and we use polynomial in T random examples. So let's review the standard Goldratt-Levin algorithm. In the input, we are given an oracle access to a function f and also an explicit parameter epsilon. We want to find all Fourier coefficients of f that have absolute value more than epsilon. And I kind of assume that you know what Fourier coefficients are. They basically correspond to the correlation of f with linear functions. What Goldratt-Levin does is that it breaks the domain of Fourier coefficients to subcubes by fixing coordinates. And if a subcube has low Fourier weight, we simply discard it. Otherwise, we keep splitting it until we get singletons. And these singletons will correspond to the high Fourier coefficients. So to get to singletons, we need to fix n coordinates, and therefore the query complexity will depend on n. So and also it requires membership queries. To make this more precise, let's say we have this subcube notation. Bits that are fixed are determined either to be in all of the sets or in none of the sets, and bits that are represented by a star will show up in all possible combination. Then the weight of this given subcube will be, so this subcube contains some coefficients. The weight of this subcube is the sum of the squared of these coefficients. So here these sets correspond to these Fourier coefficients, and we can view them in their equivalent form of bit strings. I will use the term coefficient to refer to these bit strings, and I will use the term coefficient value to refer to the actual real number that corresponds to this coefficient. As an example, let's say we have this function f, and we have this error parameter epsilon. So we want to find all of the Fourier coefficients of f that have absolute value more than, let's say, 0.1. So we start with the set that contains all of the coefficients, and we start by splitting this set by fixing its coordinates. So we go to 0 and we go to 1. So if a subcube, for example this, has high weight, here the weight is like 0.6, we keep splitting it because 0.6 is much more than the epsilon that is given to us. But if a subcube has low Fourier weight, like 1%, we simply discard it. And at the end, at the bottom of this tree, we collect all the high Fourier coefficients. Note that the height of this tree is n, and it's what we want to avoid in general in our result. Another way of viewing this same tree is using this square. So this square represents the set of all coefficients, and Goldratt-Levin does this splitting by fixing these coordinates. So this is the picture of Goldratt-Levin. Now, what if we have a prover that claims to know the top t coefficients? Can we save on query complexity? The answer is yes. Now, so we have this main theorem of this talk. There exists an interactive protocol for finding top t Fourier coefficients of a Boolean function f with error parameter epsilon, where the verifier uses polynomial in T and 1 over epsilon random examples which is independent of n. So being random examples is kind of qualitatively efficient, and because it's a weaker form of access to the input function. And being independent of n is quantitatively efficient. Towards this goal, we want to split the domain of coefficients in a different way, in a way that doesn't depend on n. So we use the following idea. So this idea also appeared in this paper, and they make some useful observations about it as well. So let's view the set of all coefficients as a vector space f2 to the n. Then let's say we choose some subspace V. And naturally, this subspace will partition the domain into affine subspaces. V here is going to be a subspace, and all the rest is going to be the cosets of this subspace. So the picture will be different based on the way we choose V. Now let's say we are interested in top 3 coefficients, like top largest coefficients of the Boolean function f. Then these coefficients are just represented by these points in this picture. And for our purposes, we would like to choose a V or a subspace V such that all of these top coefficients end up in different cosets. So for our purposes, which will be more clear shortly, the left picture is bad because it contains 2 of the top coefficients in the same coset. But the 2 right images are good because all of the top coefficients are separated. How do we actually split this domain in this way? So let's define the inner product in the usual way. We think of R as a random linear function, and we think of gamma as a Fourier coefficient or a Fourier character. Then let's say we take a small number of linearly independent linear functions. Then we can split the domain of coefficients in the following way. So 0, 1 to the n here also represents the domain of coefficients. If a coefficient has inner product with R1 equal to 0, it goes to the left side, and if it has inner product equal to 1, it goes to the right side. And the same game repeats in level 2, but with respect to R2. So in general, or as an example, but you can generalize this to other sets, V10 contains all the coefficients that have inner product with R1 equal to 1 and inner product with R2 equal to 0. Now if we repeat this for all of these S linear functions, we have now partitioned all the coefficients into 2 to the S cosets. So V0 will be a subspace and all the rest will be cosets of V0. And the height of this tree doesn't depend on n because S is small and doesn't depend on n. Now we make some useful observations about this splitting of the coefficients. So first of all, there's this Parseval's identity, which is useful in many cases. It says that the sum of a squared of Fourier coefficients is equal to 1. This implies that we don't have too many high Fourier coefficients. Another useful observation is that any 2 different coefficients will end up in different cosets with high probability over the choice of random linear functions. And by union bounding this idea, we get that all the top high Fourier coefficients will be in different cosets. They will be separated into different buckets. So I may refer to these cosets also as buckets. The third observation is that the sum of the fourth power of these coefficients in a given affine subspace or in a given bucket can be represented as this expectation that you see on the right side of equality. And this is useful because it gives us a way to estimate the left-hand side by choosing many of these, by evaluating the right-hand side many times, and by Chernoff bound, it will be a good estimate of the left-hand side. It turns out that the norm 4 of a given affine subspace will be very close to the maximum coefficient value in that affine subspace. So we have a way to estimate the maximum coefficient value in a given coset. So this takes us to an algorithm for computing top t coefficient values. So here's the theorem. There exists an algorithm that, given query access to a function f and two parameters t and epsilon here is an error parameter, and t is the number of top coefficients that we care about, this algorithm makes polynomial in t and 1 over epsilon queries to f and outputs t real numbers. These are the coefficient values of the Boolean function f, and these are the top ones. So other coefficient values will be smaller. So how does this algorithm work? So let's say this lambda t, which contains gamma 1 up to gamma t, is the correct set. That is, gamma 1 up to gamma t are the top t coefficients of f. So we split the domain to affine subspaces randomly, as we saw in the previous slides, and then all of these gamma i's will be in different cosets with high probability. And here s is small. It's like log of t plus 1 over epsilon. Then we can estimate the largest coefficient in each of these sets, and we simply output the largest t of them. The query complexity is independent of n. It's polynomial in t and 1 over epsilon. But the catch is that the coefficients or the characters that correspond to these values are unknown, because we don't have an easy way to tell which coefficient corresponds to this large value in this affine subspace. So, which takes us to the question, can we use a prover to find these coefficients? The answer is yes, we can. There is an interactive protocol for finding top t Fourier coefficients of a function f with error parameter epsilon, where the verifier uses polynomial in t and 1 over epsilon membership queries, which is independent of n. So in the end, our goal is to output the coefficients and not just the values, which are real numbers. How does this protocol work? The prover sends a set lambda t prime. So here prime kind of indicates that this set doesn't have to be the largest set, because maybe the prover is cheating and is not sending the correct set of top t coefficients. So in general, we want to handle both scenarios, where the prover is honest and is sending the correct set of coefficients, and the case that the prover is dishonest and is sending some incorrect set of coefficients. So the prover sends these coefficients. Then the verifier estimates the coefficients, estimates the values of these coefficients, which we call C1 up to CT. Then the verifier splits the domain again into these cosets. With high probability, all of these gamma i's are separated into their own coset. So what does the verifier expect to see? The verifier, in interacting with an honest prover, expects to see that the sets that contain the reported coefficients, which we show by these dots in this picture, to have large coefficient value. So the maximum coefficient in this coset should be large. And the rest of cosets shouldn't have as large as these values. The maximum coefficient value in each of the other cosets should be not too high. But when dealing with the cheating prover, there exists some large coefficient that is not reported by this prover. So that large coefficient will be in its own coset, and it's not reported by the prover. So the verifier will have a coset that is not containing any of the reported coefficients, but has a large value, large maximum value, which tells the verifier to reject. So here we used membership queries. Can we turn this into random examples instead, which is a weaker form of access to the input function? If we do, we get to the main theorem, again, which we repeat here. It's possible to do this. We use polynomial in T and 1 over epsilon random examples, which is independent of n. What is a random example? It's just an input which is sampled uniformly at random together with the evaluation of f on that input. So we developed this general framework of query to sample reduction where we delegate the task of labeling to the prover. So if we start with an interactive protocol that uses queue membership queries, given that this protocol satisfies some properties, we can turn it into a protocol where we use kind of the same amount of queries, but instead we use random examples only, or the verifier uses random examples. So recall that to find the largest coefficient in a given coset, we use the equality that can be expressed by this expectation. So what we query are these points, x, y, z, and x plus y plus z plus w. And we make this simple observation that these queries have uniform marginal distributions. So we can do the following trick. So this set of this query set, which I've written here, comes from a distribution D. And also the marginal distributions are uniform. So the verifier asks for a random example, and then she embeds this input that is given by this random example into a random location of a query set. So for example, let's say our randomness told us to embed the given random example into the third position. Then the verifier extends this incomplete query set to a complete query set that also has the same distribution D as our original query set. Now the verifier knows the evaluation of f on one of these values in this query set. So based on this image, the verifier knows the value of f at x3. Now if the prover wants to label these query points for us, and the prover wants to cheat, the verifier will catch him with probability 1/4 because the location of this known query is uniformly random in this query set. In our paper, we have also other results. Due to the limited time, I'm unable to cover all of them, unfortunately, but you can have a look at our other results. So we have general transformations. We can get interactive protocols from tolerant testers for hypothesis classes, and these are all in the agnostic learning setting. And we have interactive protocol for agnostic learning of AC0 parity with quasi-polynomial, with quasi-poly many random examples. We have interactive protocol for agnostic learning of k-juntas with order of 2 to the k random examples. And we have another result that tells if the honest prover is allowed to be inefficient, then the verifier can use a very small number of random examples to do the task of agnostically learning a hypothesis class. And thank you very much for your attention.